5.3 Area enclosed by a polar curve. Now you can find areas of enclosed by a polar curve using integration. Now the area of a sector bounded by a polar curve and the half lines theta equals alpha and theta equals beta, where theta is in radians, is given by this formula: 1/2 lots of the integral from alpha to beta of r squared with respect to theta. And you can see that area represented in the diagram in yellow over here. Now happily for us, in the formula book, you'll notice over here this formula is given. The area of a sector, that's equal to 1/2 lots of the integral of r squared with respect to theta. Now for example number 9, we have to find the area enclosed by the cardioid with equation r equals a lots of 1 plus cos theta. Now for us to do this, the way we can think about this, and we've already met how to approach sketching curves like this, we need to think to ourselves which values of theta make r positive, and that's theta being in between 0 and 2 pi. We have over here our initial line. We have here theta equaling pi over 2. So when we come to sketch, what we have first of all, if we construct a table between 0 and 2 pi for values of theta, we have a table looking something like this. Now on our calculator we have 1 plus cos theta, so we need to try out these different values of theta. So we have 1 plus cos of 0, this is equal to 2, and then we multiply this by a, so we get 2a. Then we have 1 plus cos of 1/2 pi, so we have 1/2 lots of pi, this is 1a, and then we have cos of pi plus 1, which is 0, and then we have 3 pi over 2, so here we've got 1.5 lots of pi, so multiplying this by a, we get a, and then at 2 pi, you can see here we get 2a. So if we take a look at our polar diagram, we have 2a over here, that's when theta is equal to 0. Then at theta equals pi over 2, we have a, so that's over here. Then at pi we've got 0, okay, we'll show that over here. And then at 3 pi over 2 we have a, so that goes here. And then once we go back to 2 pi we have r equaling 2a. So now we need to join all these points up. So you can see here we've got our polar equation r equals a lots of 1 plus cos theta, and our goal in this question is to find the area enclosed by this particular shape. So what's shaded over here is what we want. We want the area of this over here. Okay? So for us to find the area, what we need to do is use this idea over here. The area is equal to 1/2 lots of the integral from alpha to beta of r squared with respect to theta. Now you may think to yourself, what are the limits in our integration problem? Well, we've gone from theta equals 0 to theta equals 2 pi. And these are the half lines which we considered to help us draw this polar equation. So our limits of integration will be from 0 to 2 pi. So the area that's equal to 1/2 lots of the integral from 0 to 2 pi of a lots of 1 plus cos theta all squared d theta. So this is what we need to work out. So if we tidy this up, we've got 1/2 lots of the integral from 0 to 2 pi lots of a squared lots of 1 plus cos theta all squared d theta. So if we take this a squared outside, we have a squared over 2 lots of the integral from 0 to 2 pi and 1 plus cos theta all squared, that's 1, plus 2 cos theta plus cos squared theta. So we will be integrating this with respect to theta, and we've got over here a cos squared theta, and you may know from regular A-level maths, cos squared theta is equivalent to 1 plus cos 2 theta all over 2. So if we replace this with what we have over here, you can see we've got a squared over 2 lots of the integral from 0 to 2 pi lots of 1 plus 2 cos theta plus 1/2 plus 1/2 cos 2 theta, and we're integrating this with respect to theta. So if we simplify all this, you can see here we've got a squared over 2 lots of the integral from 0 to 2 pi, 1 plus 1/2, that's 3 over 2. And then we've got the 2 cos theta, and here we've got the 1/2 cos 2 theta. So now, if we integrate as necessary, we still have a squared over 2, and then here we've got 3 theta over 2 plus 2 cos theta. If we integrate this, we get 2 sine theta, and if we integrate the 1/2 cos 2 theta, we end up with 1/4 sine 2 theta. And we're evaluating this between 0 and 2 pi. So for our upper limit, we get a squared over 2 lots of, here we've got 3 over 2 times by 2 pi, so that will be, well, the 2's cancel, so here we're left with 3 pi And then here we get 0 plus another 0. And for our lower limit, we get a squared over 2 lots of 0 plus 0 plus another 0. So if we tidy all this up, hopefully you can see that the area is equal to 3a squared pi over 2 units squared. Okay. Example number 10, we have to find the area of one loop of the curve with polar equation r equals a lots of sine of 4 theta. Now, if we actually sketch the graph of sine 4 theta in between 0 and 2 pi, you can see the graph looks something like this. And we want where the graph is positive, so the graph is positive between 0 and pi over 4. So I'm just writing this down. So we need to consider the graph in between 0 and pi over 4. We also need to consider what happens between pi over 2 and 3 pi over 4. Okay, so we need to consider what happens between pi over 2 and 3 pi over 4. That's where also the graph is positive. It's also positive in between pi and 5 pi over 4. So the graph is also positive between pi and 5 pi over 4. And it's also positive between 3 pi over 2. And it's also in between 7 pi over 4. Okay. Now clearly at 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2 and 7 pi over 4, sine of those values are equal to 0. And at pi over 8, we've got 1. At 5 pi over 8, we've got 1. At 9 pi over 8, we've got 1. And at 13 pi over 8, we've also got 1. So if we go back here, I've just written those values down where the graph is positive. So between 0 and pi over 4. So if we think about our line theta equals pi over 2 and our initial line over here, hopefully what you can see over here, between 0 and pi over 4 is over here. Well, at 0, the graph is 0. At pi over 4, it goes back to 0. But then we said if we go back to the graph, at pi over 8, we've got 1. So if we go back here, at pi over 8, we get 1. And we times that by a. So at pi over 8, we get r equals a. So, well, if pi over 4 is over here, half of that, which is pi over 8, will be over here somewhere. So what's happening is something looking like this. Okay, so this is one loop. And just for the benefit, let's just plot everything else. Well, between pi over 2 and 3 pi over 4, so pi over 2 and 3 pi over 4 is this line. Halfway between those, we're also going to get 1. So that goes over here. So let's draw on our second petal. Something looking like this. For the next one, between pi and 5 pi over 4, through the symmetry, this is going to go here. So we get something looking like this. And now again through the symmetry between 3 pi over 2 and 7 pi over 4, that's over here. We get our fourth petal, like so. Okay, so this is r equals a lots of sine of 4 theta. And over here, we've got a value of a. Here we've got a. Here we've also got a. And here we've also got a. And what we need to do in this question is find the area of one loop. Okay, so in terms of the area we want, let's just shade it in. We only want one of these loops. Now, I could, in theory, integrate from 0 to 2 pi of this equation, and that will get me the area of all 4 loops, and then divide the final answer by 4. But if you think about it, our limits will just be from 0 to pi over 4, and that will be the area of one loop. So when we come to find out the area is equal to 1/2 times the integral from 0 to pi over 4 of r squared times by d theta. So we have over here 1/2 lots of the integral from 0 to pi over 4 of r squared, so we get a squared sine squared of 4 theta d theta. Now, if we use one of the trigonometric identities, which we all should be happy with, hopefully here you should know by now from your regular A-level maths, if we have sine squared 4 theta, that will be equivalent to 1 minus cos of 8 theta all over 2. So we will replace this with what we have over here. And if we do that, let's first of all take the a squared outside. So we get a squared over 2 lots of the integral from 0 to pi over 4 of sine squared 4 theta, which we've just said is 1/2 minus 1/2 cos 8 theta d theta. Now, what we can also do is take out the half as a common factor. So if we do that, we get a squared over 4 lots of the integral from 0 to pi over 4 lots of 1 minus cos 8 theta d theta. So if we evaluate this, we get a squared over 4 multiplied by theta minus 1/8 sine 8 theta. And we will evaluate this between 0 and pi over 4. So for our upper limit, we have a squared over 4 lots of pi over 4 minus 1/8 times by the sine of 8 times by pi over 4, so that's just 2 pi. So that will be 0. And for our lower limit, we have a squared over 4 lots of 0 minus 1/8 times by the sine of 0. This is 0, this is 0, so we're left with a squared over 4 times by pi over 4. So in total we get a squared pi over 16 units squared. So this is the area which we're after. Example number 11. For part A on the same diagram, we have to sketch the curves with equations r equals 2 plus cos theta and r equals 5 cos theta. Now, the first thing we can do, if we go to Desmos and just quickly show those sketches, I'll show the one in red first, which is 2 plus cos theta. You can see in between 0 and 2 pi, r will always be positive. So we will be constructing a table from values of theta equals 0 to theta equals 2 pi. So we have over here our table. Now all we need to do is simply substitute in the various different values into here and see what we get for R. So if we grab our calculator, you can see hopefully here we have 2 plus cos of 0, that's equal to 3. 2 plus cos of 0.5 pi, that's equal to 2. And then 2 plus cos of pi, you can see this is equal to 1. Cos of 3 pi over 2, so here that's the same as, well, what's 2 pi? We'll do this first. That's 3. And then 3 pi over 2, so that's 1.5 pi. That's equal to 2. So we now need to sketch our polar equation. So if we do that, let's just plot the points first. We've got 3. That's when theta is equal to 0. Then for pi over 2, so here we've got our initial line. Here we've got theta equals pi over 2. So then when we've got pi over 2, we get 2. So that's shown here. Then when we got pi, we've got 1. And then at 3 pi over 2, we get 2. And then we go back over here. Okay? And now the next question is this a dimple or is it an egg shape? So just as a reminder of what we said earlier in a previous video, we've got an egg shape when we've got this condition and a dimple shape when we've got this condition. So first of all, here you can see P is equal to 2 and Q is equal to 1. So let's just write this down. P equals 2, Q equals 1, and therefore 2Q is equal to 2. And what you'll see over here is this P is greater or equal to 2Q, which is 2, and therefore here we've got an egg. So if we sketch all of this out, you can see here we've got this curve over here, so let's just label it. We've got over here, if we add in these values while we're at it as well, here we've got 3, here we've got 2, here we've also got 2, and here we've got 1, and this is R equals 2 plus cos theta. Okay? So what we now need to do, in a similar way to what we did with the other equation, we've got R equals 5 cos theta. We first of all need to see which values of theta we need. So if we go back to our sketch, as we see over here, let's just hide this for now. You can see here where R is positive is in between 0 and pi over 2, and also in between 3 pi over 2 and 2 pi. So let's just write that down. So we need to consider the values in between 0 and pi over 2, and also values in between 3 pi over 2 and 2 pi. So now we need to construct two tables to help us do this. So I've drawn the two tables, and if we go to our calculator, we've got 5 cos of 0, that's equal to 5. And then we've got 5 cos of pi over 2, that's equal to 0. Okay. And then for 3 pi over 2, we've got 0, and then it loops back down to 5. So in terms of what this will look like, we've got a value here at 0. We've also got another value here as well. So let's plot these. So the curve looks something like this. Here we've got 5. Here we've got 0. So this is r equals 5 cos theta. Okay? So that's how we approach part A of the question. For part B of the question, we have to find the polar coordinates of the points of intersection of the two curves. So for part B, to find the points of intersection, we set this equation equal to this equation. So if I call this 1, and I call this 2, setting 1 equal to 2, we've got 2 plus cos theta equals 5 cos theta. So rearranging, we've got 4 cos theta equals 2. Cos theta is equal to 1/2, therefore theta is equal to plus minus pi over 3. So when theta is equal to pi over 3, we've got 5 lots of the cosine of pi over 3, which is 5 over 2, and of course minus pi over 3. That will also give the 5 over 2 because cosine is an even function. So therefore, r is equal to 5 over 2. So therefore, the coordinates of intersection, so the coordinates of intersection point, that will be given by 5 over 2 and plus minus pi over 3. So that's how we approach part B of the question. Now for part C of the question, we have to find the exact area of the region which lies within both curves. So I've shown that over here in green, we need to find this green area over here. Now, if I show you this sketch in just a bigger format over here, so we'll do part C over here actually. We want to find essentially this area here. Now, if we label our curves here, this curve shown in blue is r equals 2 plus cos theta, and the one shown in red over here is 5 cos theta. Okay, and of course here we've got the initial line, and here we've got theta equaling pi over 2. Now, the way we can think about this, hopefully here you can see, we've got a half line over here, we've got pi over 3, and here we've got another half line, okay, minus pi over 3. Now, to find out this area, this total area, hopefully you can split this up as shown over here. So what I'm doing is just splitting the area we want to find into two other segments. And you'll see why I'm doing that. And notice I don't go below the initial line. That's because eventually I'm going to multiply by 2 because the area on the top is the same as the area on the bottom of this initial line. So we've got this bit in orange, okay? And then we've also got the bit in between here as well, which I'll show in pink. We've also got this bit in pink over here as well. And of course that corresponds to this bottom bit over here. Okay, so this is what we have so far. So in terms of us finding the area, if we split it up like this, hopefully you can see this green area, which we mentioned over here, is basically these two areas twice. So for part C of the question, the way we can approach part C is to, well, let's just write it down. The area is equal to 2 lots of 1/2 lots of the integral. Now here, if we consider this bit in orange, we're going from 0 to pi over 3. So we've got 0, pi over 3 here, and the curve is 2 plus cos theta all squared. And we're integrating this with respect to theta. And then we've got this bit over here, which goes from pi over 3, okay, to pi over 2 over here. And that makes sense if we think about the table which we mentioned earlier over here. Okay. So with that, we add on 2 times by 1/2 of the integral from pi over 3 to pi over 2 of 5 cos theta all squared d theta. So what we now need to do is, well, let's just show you which bits correspond to what. We've got this bit over here, which is the bit in orange, okay? So let's just show that. So this over here is what we have in orange, and then what we have in pink is this bit over here, okay? So the reason we multiply by 2 here and here is because the bit on the top is the same as the bit on the bottom. So having done all the complicated work, the rest is just simple integration. So 2 times by 1/2, that's just 1. So here we've got the integral from 0 to pi over 3. Now if we expand this out, we get 4 plus 4 cos theta plus cos squared theta d theta. And here 2 times by 1/2, that's just 1. And then we add on the integral from pi over 3 to pi over 2 of 25 cos squared theta d theta. So what we can now do, well, if we recognize that cos squared is the same as 1 plus 1 plus cos 2 theta all over 2, and then we add this 4 to it, what we have is the integral from 0 to pi over 3 of, well, we'll write it out in full. We've got 4 plus 4 cos theta plus 1/2 plus 1/2 cos 2 theta d theta, and then we've got this pi over 3 to pi over 2 of 25 times by 1/2 plus cos 2 theta. So that is what cos squared is. And don't forget we've got the d theta as well. So if we tidy this up even further, we've got the integral from 0 to pi over 3 of, well, here we've got 9 over 2 plus 4 cos theta plus 1/2 cos 2 theta d theta. And then we've also got 25 over 2, lots of the integral from pi over 3 to so what I've done over here, well, here we need the half as well. So here we've got pi over 2, and then here we've got 1 plus cos 2 theta d theta. Okay, so now we need to tidy all of this up. So here, if we work this out, we've got 9 theta over 2 plus 4 sine theta plus 1/4 sine 2 theta. We're going to evaluate this between 0 and pi over 3. And then we've got 25 over 2, lots of theta plus 1/2 sine 2 theta in between pi over 3 and pi over 2. So if we substitute everything in, we've got 9 over 2 times by pi over 3, that will be 3 pi over 2. So here we get 3 pi over 2 plus 2 root 3, because sine of, we've got 4 times by the sine of pi over 3, so here we get 2 root 3, and then here we get root 3 over 8, okay, minus the 0 plus 0 plus 0. So what I've just done over here is work out the upper limit, and then for the other one, if I multiply the 25 over 2 into the bracket as well, we've got 25 over 2 times by pi over 2, so here we get 25 pi over 4 plus, well, half times by sine of pi, because we've got 2 times by pi over 2, that's just 0. And then for the lower bracket, we get 25 pi over 6, and then we've got sine of 2 pi over 3 times a half, so we add on 25 root 3 over 8. Okay, and you can double check your answers with the calculator. So if we collect like terms, we get 43 pi over 12 minus root 3 units squared. So this is our final answer of that shaded bit which we wanted to find.